Okay, so we've introduced the ideas of the metric, the first fundamental form, and the second fundamental form, how the surface is embedded in R3. So let's look at some examples. We did a lot of algebra last time. We set up a lot of formalism, and now I want to illustrate it in some concrete examples so that we have a little fun and learn the formalism somewhat better. So let's look at parametrizing surfaces. And the first one we'll look at, let's look at a torus. Okay, well, how do I make a torus? I want to parameterize it in a natural and simple way. And so it's clearly a surface of revolution. So let's begin at the beginning. What do you revolve? Well, you take a circle of radius r at a position A in the x direction. Make sure that A is larger than R, of course, and then rotate that circle around the z-axis. Okay, that's easy enough to do. Well, the circle before it's rotated, the curve before it's rotated, is written in x, y, z Cartesian components as in the x direction. A point P on the surface is, well, let's see, you go out a distance A, and then you go out an additional distance R cosine theta. Okay, the y position is 0. Y is going to be perpendicular to x. We'll rotate into it. We begin with a figure in 2 dimensions. And then in the z direction, well, what's the z coordinate of the point P? Well, it's just r sine theta, as we see from the picture. Okay, so now let's rotate it around the z-axis to an azimuthal angle phi. Okay, then the point P becomes a point on r of theta and phi. And what is that? Well, originally point P had an x component of a plus r cosine theta. Now we rotate it through an angle phi around the z-axis, and so that distance is diminished by a cosine phi. At the same time, we pick up a y component, which is just this times sine phi. And the z component, of course, is left unchanged by the rotation around the z-axis. So there you have it. There's the torus. Okay? Okay. And so it has a radius r of the circular frame of the torus, and it has a radius a of the bulk of the torus, like that. Oh, now, so I want to calculate some the character of this surface, okay? And so I know I have to calculate the first and second fundamental forms. Okay, so I need the derivatives, r sub theta, r sub phi, r sub theta phi, etc., etc. Okay, and I just plug those into our previous formulas for EFG and lowercase EFG for the second fundamental form. So it's easy to do that. And I get capital E is r squared, f is equal to 0, and g is equal to a plus r cosine theta quantity squared. And so dr squared, the metric, is r squared d theta squared plus a plus r cosine theta quantity squared d phi squared. I did that in a mechanical way. I can do that for any surface once I have a good mesh on the surface and be able to calculate the first and second fundamental forms. But of course, this answer I could have guessed. I could just look at the thing and figure it out. We would have guessed this because here, dr squared consists of 2 terms. One is r squared d theta squared. Well, r d theta is just a line element around the circle of radius r. That's easy. And then the second term, okay, a plus r cosine theta quantity squared plus d phi squared. Well, a plus r cosine theta, that's the distance of P from the z-axis. D phi is the angle around the z-axis, and so this object here squared, well, it's the line element of circle swept out when P is rotated around the z-axis. So clearly that's the metric. Either do it by plugging in or do it by making a picture. Either way, it's good to have the general formulas around because sometimes we'll have surfaces that are more challenging. And then now I can compute various things. I'm particularly interested here in the metric. Okay, we're going to be emphasizing in the lectures the intrinsic properties of the surface, and that's the metric and the Gaussian curvature, for example. I'll have less to say about the second fundamental form, okay, and the mean curvature, because those have to do with how the surface is embedded into R3. But those things are interesting quantities as well. It's just from the perspective of preparing ourselves for Riemannian geometry and intrinsic geometry of surfaces and space-times, we're emphasizing certain aspects of classical differential geometry and not everything. Okay, now I can also calculate the second fundamental form and find that little e is r, little f is 0, and g is cosine theta times a plus r cosine theta. Now I can do various things. I can calculate, for example, the Gaussian curvature. Well, that's the ratio of the determinants of the second fundamental form to the first fundamental form. Well, that's easy because you see the off-diagonal elements are both 0, so it's just EG over EG, capital. Okay, and so I plug in, I get cosine theta divided by r times a plus r cosine theta. Okay, that's fine, but it's a little bit peculiar because there's a lot easier ways to get the Gaussian curvature from a simple surface of revolution. The easier derivation is just to identify the principal directions and the eigenvalues for those principal directions and just take their product. Okay, well, here is a torus, okay, and so clearly I want to find the principal direction at a point P, let's say this point, okay, which is minimal, okay, and then the principal direction which has a maximal curvature as well. And so clearly for the maximal curvature I want the circle of minimum radius because the curvature is 1 over that, and so I see that the blue line, just the radius around the body of the curvature is the 1, and so the radius of that circle of radius r is just 1 over r. Okay, now when I calculate K1 and K2, remember those are the normal projections of the curvature to the surface. But in this particular case, you see, here's the body of the torus, shown here in blue, shown here in red, and I see that the curvature points in the radial direction. Okay, so K1 is in fact just the curvature of the circle. That's just 1 upon r. So there's no additional geometry to be done in that particular case, because at the point P, the curvature of the curve around the torus is in the radial direction, okay? And so the dot product of the curvature and the radial direction is just 1. Cosine of the angle between them is cosine of 0, which is 1. Okay, and then next I have to find the radius here. Let's say I'm at this particular point, and I want to find the direction which has the minimal curvature, and clearly that's going to be a circle that goes all the way around the rotated circle, the torus. Okay, clearly that fellow to the point P has the largest radius and the smallest, therefore, curvature. The radius of the circle from P to the z-axis. So here it is. I'm showing here as a cross section of the x-axis and the z-axis. How far is it from the z-axis? What's the radius of the circle around the torus? Okay, well, it's a plus r cosine theta. We've already looked at that from several different points of view. Now that's a circle. It has a curvature which points along its radius, so it's perpendicular to the z-axis. I've written that here as kappa, okay, n hat, little n hat. I see that points at a direction skewed from the normal by an angle theta, as you see from the picture, okay? And so I read off that the projection of the curvature onto the normal, right, that's the kappa sub n, that's the second fundamental form, that's the K2, the eigenvalue of minus n prime. I read off that n, capital N dot little n is cosine theta, okay, and so kappa 2, K2 is equal to a cosine theta divided by the radius of that circle. Okay, I take the appropriate dot product of kappa little n hat. Okay, the curvature of this of the curve, the circle, it goes through P. It has a curvature that goes in the kappa little n hat direction. Okay, I'm supposed to take the dot product of that with a normal to the surface to get the kappa sub n, and so that gives me a cosine theta upstairs and this distance downstairs, and that's the principal curvature, the second one. K2, the smaller of the two. We note that K1 of E1 dot E2 is equal to 0, and okay, and we now we take the product of K1 times K2, and I reproduce the formula that I got by doing the various other derivatives and calculated directly from the ratio of the determinants. So instead of doing the ratio of the determinants, I could just look at the principal curvatures and take the determinant as the product of the two principal curvatures and get the answer that way in a more intuitive and easy fashion, and there you have it. Okay, well, what do we notice? Well, we notice it as a cosine theta up top, okay, and so K is greater than 0 on the outer surface of the torus, the outer surface out here, where theta ranges from minus 2 over pi to pi over 2, where cosine theta is positive, and K, the Gaussian curvature, is negative on the inner surface, okay, where cosine theta is negative. And so I show that on the picture here. On the outer part, the outer 180 degrees of the torus, the Gaussian curvature is 0. As I get to the top or the bottom of the torus, the Gaussian curvature becomes 0. Right? It becomes 0 because cosine of plus or minus pi over 2 is 0. Okay, in those particular positions, the curvature vector of the large curve that goes around the torus is perpendicular to the normal, and so K2 vanishes there, and so the Gaussian curvature vanishes there. The top of the torus is flat, the bottom of the torus is flat. And then I come inside the torus, as shown here, inside for that 180 degrees here, and I find that K is negative. Okay, K is negative because cosine theta is negative for theta in that region. Okay, and now I can make sense of that. Why is the Gaussian curvature positive on the outside? Well, I see that the Gaussian curvature is the product of K1 and K2, and both of those curves have the same sign for their curvature. They both curve in the same direction. Okay, but if I go inside the torus, I see that one of my principal curvatures curves outward, and the other one curves inward. So K1 times K2 is negative. Okay, and that's just tracked by the fact of the cosine theta up in the numerator. Okay, but we also see that the inner surface is saddle shaped, right? It's saddle shaped. Okay, in one direction, it sweeps around inside in here like that. The other direction over here, it sweeps to the outside. So if I have a tangent to a point inside the torus, there are points therefore on that on both sides of the tangent plane. Around here, they're on the outside of the tangent plane. Around here, they're on the other side of the tangent plane. Okay, if I have the outside of the torus, I slap a tangent plane on it, then I see that the entire surface is on one side of the of the tangent plane. So I have a clear distinction between kappa positive and kappa negative. Kappa negative looks like a region where I have a saddle point. Okay, and we'll want to understand that, and we'll take some examples which bring that out rather clearly. Okay. So now let's look at a general surface of revolution. Okay, not the particular case of a torus. So I'll have here a curve in the xz plane, which has a height h of s and a radius rho of s, and I'm going to let s be the arc length of the curve c. And I'll take that as my curve, and then I'm going to rotate it around the z-axis, make a surface, and understand the geometry of that surface. Okay, fine. So for the curve here in the xz plane, I know that its position xyz is just rho of x, rho of s in the x direction, 0 in the y direction, and h in the z direction. Okay. I'm going to choose rho positive, of course, so that it is a meaningful curve to rotate. And then I'm also going to parametrize it with the arc length. And so rho prime of s squared plus h prime of s squared, okay, is just this quantity, which is 1. Okay. Upstairs, I just have the arc length written out in rho and h. Downstairs, I have the arc length squared. So they cancel, and I get 1. So it's a curve. I would say that it has unit velocity, okay, or in this particular case, the identity rho prime squared plus h prime squared is equal to 1. Arc length is often a very convenient way to parameterize curves for theoretical discussions. If that's not convenient in an application, I'll have to use the chain rule, to transform to a different parameter, and I can do that. The formulas get a little more complicated, and so I like to emphasize arc length as being handy from the theoretical point of view. Okay, so that's what we'll do. We'll rotate this curve around the z-axis through an azimuthal angle phi in the standard way we did with the torus. All right, so I have a y-axis over here. This curve gets rotated in the xy plane through an angle phi, the azimuthal angle phi. And so r of s and phi is just the rotation of this fellow through an angle phi. So rho of s goes to rho of s cosine phi. 0 goes to rho of s sine phi. That's the component in the y direction. Okay, proportional to the sine of y, the projection of the rotated radius in the y direction. And then, of course, the rotation around the z-axis doesn't change the height. H of s, h of s. Okay, great. I have a nice parameterization for the curve. My mesh is s and phi. And I can calculate all my derivatives and calculate my first and second fundamental form. So that's what I do. So I calculate the first fundamental form is E is rho squared, F is 0. Aha, that's nice. Okay, the coordinate system, the mesh is orthogonal, or is like that. That simplifies things. And then G I calculate is rho prime squared plus h prime squared. But that's just 1 because I'm using a coordinate system in which one of the coordinates is arc length. So I calculate that dr squared is E times phi squared. Okay, so rho squared times phi squared. And G is 1, so the other term is ds squared. Okay, now that's easy, and of course, again, I can read that right off of this figure. I don't need all of this formalism to do that, but maybe I'll need this formalism to make further progress. In particular, the second fundamental form, you should calculate this. Okay, little e is this collection, little f is 0, that's handy, and little g is that collection of derivatives. So just check me on that. Okay. Now then I can calculate the Gaussian curvature. Again, the Gaussian curvature is kind of easy in this case because capital F and little f are equal to 0. So these terms cancel, and I just have simple calculations to do. Okay. And so I do those calculations, do a plug-in, and here it is. Looks a little complicated, but it's not really that bad because I want to use the fact, okay, that rho prime squared plus h prime squared is equal to 1. I haven't used that yet. Once I put that into the numerator, I find that the numerator simplifies to just simply the second derivative of rho with respect to the arc length. Okay, so check the algebra in supplementary lecture 9. It's just a single line. I don't want to do it here. Okay, and just check that the Gaussian curvature becomes that. We use that that rho prime squared plus h prime squared is 1. Take its derivative with respect to s. Get some identities between h prime and rho double prime. Put them in there, and the numerator just comes down to rho double prime. That's nice. So now I see a simple formula for my Gaussian curvature. If you give me rho, I'll give you k. I'll just take minus rho double prime divided by rho. Okay, it doesn't depend upon upon h. Well, that's very much a matter of choosing the arc length as a parameter for my mesh, because that enforced that rho prime squared plus h prime squared is equal to 1. So I can trade rho prime for h prime wherever I want to, and if I do that, I can then write the Gaussian curvature is minus rho prime over rho. Okay, so I can write that then as a differential equation. The second derivative of rho with respect to s plus k is equal times rho is equal to 0. Okay, so I can look at this from various different points of view. If you give me a rho, I can then calculate Gaussian curvature at any point. Okay, that's good. But you might instead give me a k. Okay? You might give me a k and tell me that the surface is a surface of revolution, and then I'll tell you what that surface is, because I'll calculate rho from that, and then I'll calculate h from that, and I'll reconstruct it. Okay, that's interesting. The Gaussian curvature, okay, tells me the shape of the curve. Well, of course, it's a differential equation, so I'll have to supplement it with some boundary conditions, and they might distinguish between different alternatives. Keep that in mind. Okay, but that's interesting. In a typical problem, the metric, okay, or the Gaussian curvature, isn't enough to specify the surface. I also have to know the second fundamental form as well. And I can think of lots of examples of that. Let's just say k was equal to 0. Okay, what's the surface? Well, a plane has no curvature. That's fine. But then, in addition, there were other surfaces that had no curvature. The cylinder has no curvature. The cone has no curvature as long as I'm away from its ends, its singular point, its point. Okay. Okay. So in those particular cases, the curvature tells me the local properties of the surface, but the global properties, how it's embedded into the space, come from the second fundamental form. So we should keep that in mind. This is an interesting differential equation. Let's say, for example, that k was equal to 1. That's one of the few differential equations I can solve by sight. That's a harmonic oscillator. Okay, and so in particular, in that case, I can find the sphere. Okay, I could, for example, just take, if k is equal to 1, then the second derivative of rho with respect to s squared plus rho is equal to 1. Well, that's solved by sine of s. Okay, and so instead of having this funny general curve here, I would just have a sine of s like this, rotated around. That makes me a sphere. Okay, and so that's an interesting solution. You might have the case where k is equal to -1. That's not solved with harmonic functions. That's solved with hyperbolic functions. Okay, and then we'll generate a Gabriel's horn Okay, and we'll study that case because that's given by hyperbolic geometry. So we'll get to that eventually, but that's an interesting set of points. Well, since little f and f is equal to 0, the formulas for k and h simplify. They reduce down to this. Just plug little f and capital F equals 0 in the previous cases. Okay, so capital K was the product of k1 and k2, and h was the average of k1 and k2, so it doesn't take any imagination to see that the solution for the principal curvatures is just k1 is little e over capital E, k2 is little g over capital G, and here are the formulas in terms of h and rho. Okay, and so there you go for the Gaussian curvature and the mean curvature as well. Okay, so that's an interesting example, and it's discussed further in supplementary lecture 9, and we'll take a look at that. But I want to turn now to the surface of a graph, and we'll pick that up next time.